Well, very good morning if you are on the left-hand side of the Atlantic, and good afternoon if you are on the other side of the Atlantic. Thank you very much for to Conrad and all the colleagues from the IEEE for this kind invitation, and especially Conrad for these beautiful words, so kind to me. Thank you. Well, what is the topic today? I have a very short presentation for you. It's regarding analyzing future power systems, and in particular, we are dealing with several of the tools that we can use for that job. Specifically, CoSimulation, real-time simulation, and also hardware in the loop. Okay. Before I start this formal presentation, I would like to do a short disclaimer here. I would like to say that all the opinions in these sessions, they belong to me, and I am totally responsible for any opinion that I present here, okay? Another quick comment is that all the slides will be available as usual in my ResearchGate repository, and also the video will be also recorded in 4K high resolution, and you will be able to download that video or watch that video later in my YouTube channel. Okay, I highly suggest that you open an account and be involved in ResearchGate. It's a social media for academics, and it's a very good channel that you can get very valuable information. Okay, what is the plan for today? Well, to be honest, the agenda is longer than I expected. I will start with some general concepts. I am sure that many of them you are aware about those concepts and also very familiar. Then I will go for different type of simulations that we can use in electrical power system. My presentation will be focused mainly on electrical power system. However, few of the ideas can be extended for any other kind of system, for instance mechanical or electrodynamics or any other kind of systems. Okay, then I will discuss digital simulation in electrical power system, starting with what we call offline simulations. That historically was the first type of simulations that we use in electrical power system. Then I will go for CoSimulation, then real-time simulation, hardware in the loop, and I will spend a few minutes talking about practical cases related with the lab, and finally some closure. Okay, let's start with very basic concepts. Okay, the first thing that we need to understand is that from the control theory point of view, we want to think about any kind of system as a set of devices that they are interacting each other, and those devices, they have a very specific objective, and the situation is that those systems that they have several components interacting each other, they must follow some kind of rules. In some cases, we use mathematics to define those rules, and those rules are defined in the way of equations. Okay, for instance, electrical power systems, as the name say, is a system. In this case, is a massive infrastructure designed to deliver electricity to the customer, and we can subdivide that huge infrastructure, the electrical power system, in so many other subsystems. Okay, for instance, we can talk about the electrical power system of this huge infrastructure, but then we can talk about the generator unit as a subsystem inside the huge infrastructure called electrical power system. In this case, the system is involved, or let's say surrounded by an environment, and there are some classical boundaries and structures defining how the system must behave. Okay, from this slide, what I want that you understand is that electrical power systems, they are huge, They are complex, and we need to define those rules that in some sense define the unified performance, the unified behavior of the system, okay? Dynamic systems, they are basically systems that they evolve over the time. And the truth is that the electrical power system is a dynamic system. In those dynamic systems, we have input signal, perturbations coming from the environments, or some changes that they are coming in natural way, okay? In those dynamic systems, we need to use some mathematical representation, and the typical way to do that is using mathematical equations, okay? What I'm trying to tell you is that dynamic systems, we use to model those dynamic systems considering what we call input variables and output variables, okay? In those cases, the equations relating inputs and outputs, they define the dynamic of the system, and we call those very specific variables defining the behavior state variables, okay? In electrical power system, depending on the objective of the study that you are enforcing, you will have different type of state variables. However, I will not go in full detail here about state variables. However, what is important for me that you understand is that those representation, those mathematical representation have huge impact in the way that the later we solve the equations and the way that we present the results. The classical way to represent a dynamic system as the electrical power system is the use of what we call differential algebraic equations. From control theory, we took this idea of using differential algebraic equations. In a differential algebraic equation, we have two clear sets of equations. One set of equations that they have the derivative of the state variable, and basically what is describing is how the state variable changes inside the system. And then there are some connecting variables that we call the algebraic variables, and those algebraic variables are representing connections and relationship between components, okay? And I am talking about this because it's very important from the simulation point of view, because this differential algebraic equation has some mathematical properties that they allow to create a very specific tool to solve the equations. What I'm trying to say is for many years, electrical power engineers has been using what we call time scales in dynamic processes. It's very clear that inside electrical power system, there are phenomena that they have some duration or they have some time scales. We have phenomena that they are extremely fast, like the lightning strikes, but also we have very slow processes like the thermodynamic process involved in a boiler. What I'm trying to tell you is that these time scales, they have different properties. One of those properties that allow the separation of the phenomenon using the time constant related to the phenomenon. And that is very important, because the electrical power system is typically a physical system. When we write this differential algebraic model, we are creating the equations that define the dynamic behavior, and when we have those equations, the next step is solve those equations. And there are two different possible solutions from the mathematical point of view. We can have closed form solutions. We want to have that because that describes the family of functions that define the system. However, in reality, electrical power system, they are complex because the size, because the interactions, the coupling between the variables, and as consequence, we need to use numerical approximation, numerical solutions to get the dynamic of the system, okay? But coming back to the time scales, the time scales are very important because allow to me define the very specific set of equations that I want to solve and the very specific method or algorithm to solve that. There is a general assumption that we use when we are using those time scales. We have a very specific phenomenon that we want to study. For instance, if we are interested in power system stability, we go for electromechanical phenomenon. And the electromechanical phenomenon have a very specific time constant between 10 seconds and 100 milliseconds. What we will do when we use these time scales is that we say all the phenomena above this time are neglected, and below that also are neglected, and we are focusing just in this time scale, okay? However, those time scales, they are extremely important because they define the different type of simulations that we can find in a classical power system. Using the concept of time scale separations, there are two classical studies that we use for time domain analysis of dynamic processes in electrical power systems. One of them is concerned what we call root median square Rms simulation, and the other set of studies is what we call electromagnetic Tracian simulations. In Rms simulation, the main interest is the electromechanical interaction related with the synchronous machine. But on the other hand, the electromagnetic Tracian, the Amt simulations, are related with phenomena that they are extremely fast energy interaction between capacitors and inductors, and that is a very interesting point of view. The Amt simulation, as the name say, they concern about electromagnetic transients. And one very specific, very particular property of this study is that when we are solving the equations, we are doing time domain simulations and we are obtaining the instantaneous value of the electrical variables, okay? But the bad news here is that we need to represent all the dynamic of every single component inside the electrical power system. And that imply or that require that we use high order model for any equipment or any device inside the electrical power system. And as those models are high order, we need to use an integration step, the mathematical tool, to solve the problem with a very, very small time step, okay? The good news here is that this is very, very useful, especially if you are interested in switching over voltages, short circuit currents in details, in rush currents, and so on. Bad news from the mathematical point of view, you need to use a lot of differential equations, and you are obtaining, in this case, the instantaneous value of the electrical parameters, okay? On the other hand, we have the electromechanical phenomenon, and we use what we call the Rms simulation. In the Rms simulation, we care about voltages and current, electrical quantities, and those electrical quantities are represented by phasors. To be honest, this is a very good simplification that allow us to solve the problem in a very simple way. We assume that the inductors and capacitors are represented by reactances, and from there, the use of concept of impedance and phasors allow a very good solution. In this case, the dynamic that we are interested for is basically the dynamic related with the synchronous machine, controllers, and mechanical devices. The good news here is that we can use a larger time step integration that is computational not so heavy as the Amt. Okay? Here you can see that from the mathematical point of view, we are representing the components, resistor, reactance, and capacitance using a linear representation, algebraic representation, and we reserve the use of differential equations only for electromechanical systems, okay? Now, why I am telling about equations, differential equations, algebraic equations? Because power engineers, we don't have the possibility, it's very rare that we have the possibility to go into the field and run a test in a real power system. What I'm trying to tell you is that because security and reliability, we cannot put a short circuit in the system, in the real power system, and then measure the short circuit current. That is unrealistic. For that reason, for many decades, electrical engineers have been trying to use different tools to obtain the electrical quantities that we use in the studies, in power system studies. Historically, the first simulator that we have in electrical power system is what we call the Tracian network analyzer. The TNA is probably the oldest simulator that we have. Early 1929 in the MIT, they create this TNA. okay? This is basically like a huge Legos that you have transmission line, you have a small generators, a small transformer, and you interconnect that. Okay, this was very, very used for many decades, but when the Second World War started, these TNA start to be old, and then the sudden rise of the digital computers start to put down the TNA, and then start to be dominant. Okay, 1940s, 1950s was probably the starting point of using digital computers, and finally large digital computers start to be available for 1950 for electrical power system analysis, including load flow programs and short circuit calculations, and the last one was power system stability analysis. Okay, as an example here, I would like to show you some very important ideas about how important the simulator is. Here I will present to you some digital simulations regarding power system. We call this kind of simulations offline because the analysis is totally off the grid and is basically performed inside a digital computer. The simulator or solver is basically the algorithms and the program that we use to solve the differential and algebraic equation model. Okay, for instance, there are many commercial software available. Also, they are open access software, but in this case I am using one of my favorite, the Excellent Power Factory. Okay, and those software, they have the models of every single component already predefined inside, and when you interconnect the different components, you are creating the set of differential algebraic models. Okay, then the software have appropriate methods and algorithms and numerically solve those equations. Just to show you how important and how different RMS and AMT simulations are, I would like to show you this very specific case. Here we have a photovoltaic power plant connected what we call an infinity bus bar, and there is a short circuit in the transmission line number 1. Okay, in this case we are using a voltage 3-phase short circuit, and that short circuit is inserted in that transmission line. Here I have the time domain response. As you can see here, we have the graphical representation of the voltages on the top and the currents at the bottom. Okay, and I am presenting in both plots what we call the result for the RMS simulations and the AMT simulation. Okay, as you can see here, let me use the laser pointer. The green line represents the RMS solution, and you can see there is a straight line over here because we are representing just the RMS value. Okay, this is obtained from the RMS simulation. And on the other hand, we have 3 sine wave, very clear sine wave, that during the short circuit they reduce the size because we have a voltage drop during the short circuit. And then after that, we have a recovery period for those sine wave. However, what is important here to see? What is very important to see is that when we are using AMT simulation, we are obtaining the instantaneous values, and those instantaneous values, they have huge information, a lot of information regarding what is happening very fast inside the system. But if we use the RMS value, we simplify the equations, we avoid so many fast dynamics, and the information that we are getting probably is useful for some studies, but for others not so much. And that is my general conclusion in the next slide. Okay, let me show you in the next slide what is happening when we compare the results using RMS AMT simulation. Okay, for instance, in the top left hand side, you can see the active power. As you can see, in a steady state, the RMS and the AMT simulations, they have the same value. And also here, during the short circuit, during the steady state behavior, they have the same value. But if we are interested on the stream values during the fast Tracian, you can see the huge difference. For instance, if we go here to the bottom right hand side, you can see how the AMT is presenting a huge short circuit current during the starting point that is around 1.5 per unit, but if you compare the peak value of the RMS current, it's just reaching 1 per unit, okay? What I'm trying to tell you is it's very important that we understand that AMT and RMS, they are very different. They contain very, very different information. And right now, with the penetration of renewables and power electronics, it's very important that power engineers start to think about the use of Amt simulation. Also, what I would like to point out is that electrical power systems are becoming more and more complex, and the complexity is coming in many directions. One is historically clear, and it's the number of components interconnected. A huge power system has so many bus bars, so many generators, so many controllers that from the size point of view is a challenge. But also the integration of so many technologies in the physical layer, in the software and the network are creating massive challenge, okay? Today, we are talking about smart grids. Well, probably a couple years ago, we were talking about a lot of smart grid. Right now, we are talking about digital energy system. What I'm telling you is that information, communication, and technology is inside the electrical power system and creating and acting very, very fast inside the system, changing the way that we are using the system, okay? In that sense, including physical, software and network layers, communication layers, we need to take new actions, new way to solve the system, okay? One of the possible ideas to solve a multi-mode system is the use of what we call CoSimulation. CoSimulation is nothing new. CoSimulation has been in science for many years, especially in the automotive industry and also in aerospace industry. And CoSimulation is basically when we divide this huge system into several subsystems and we solve those systems in a distributed manner. There are very good features that we can take from these advantages that we can take from this feature, okay? We can have what we call a master. The master is controlling the solution of the differential algebraic models for different subset of components. For instance, we can imagine the top one here like the physical layer inside the electrical power system, including generators, transformers, transmission lines, and so on. Then we have an informatic layer including all the cybernetic components, and finally we can imagine the last one of those slaves like the layer component all the communication systems, okay? Again, CoSimulation is something that is not new. If I told you about my favorite software, the Excellent Power Factory, the Excellent Power Factory already includes the possibility of using CoSimulation. And CoSimulation can be think in different ways, okay? The CoSimulation that I was talking in the previous slide, it was a multi-domain. When we have physical domain, we have communication domain, and we have a cybernetic domain. But also inside electrical systems, we can try to have two different types of domain. We can have, for instance, simulations including one side of the system in RMS, and you have interest on very fast phenomenon, and you have another part of the system that you have a very small processes, slow processes, and you can use Rms simulation. This is something that is already included in the Excellent Power Factory. Also, we have presented that there are many other interfaces that you can use to integrate different subsystems. The Excellent Power Factory uses different communication protocols and different ways to communicate with third-party applications. For instance, one of the favorite ways that people want to do CoSimulation is using the integration of the Excellent Power Factory and MATLAB. For instance, if you are interested on modeling and simulating a huge network, for instance, the continental European power system, you can use Power Factory and you can use the tool in Rms Simulation. But if you are interested, for instance, on integrating hydrogen, hydrogen is another domain, and if you want to replicate the behavior of those electrolyzers and all the pipes and all the pumps and all the storage related with hydrogen, you can use another software more adapted for this kind of modeling and simulation like MATLAB. And using just an interface between those software, you can establish the communication. Today, more of the electrical power system analysis software, they open the door for doing CoSimulation. However, something that you must realize is that typically this CoSimulation is offline. That means that the time is not necessarily the main variable creating the process inside the computer and the other clients in the system, okay? Well, but electrical power systems, as I said before, they are becoming more and more complex. And the idea that they are becoming more and more complex is coming from the issue of integration of many technologies, okay? These technologies, including physical layer like generators, PV systems, electric vehicles, and so on. But also we have two very important layers right now. One of them is networking. We have a lot of very fast or low latency digital communications, and also we have a lot of new technologies coming from computer science like artificial intelligence, machine learning, and so on. Now, the complication is that we have multi-domain simulations that we need to take care about. And in those multi-domain systems that we call cyber physical systems, the synchronization and the time is very important when we are solving the differential algebraic model. And that is the reason that in electrical power system, few years ago, we start to use the concept of digital real-time simulation. And what is digital real-time simulation? Well, digital real-time simulation is, I will summarize in a very simple way, is solving the differential algebraic model, but where the time is the same time that we have in real time. Let me explain this. Many years ago, if we need to run a simulation in power electronics, you can use a software, for instance, like MATLAB Simulink. And because you are running this simulation offline and you want to assess 10 seconds of real life, you press the button and you run the simulation, and this simulation can be solved probably in 30 seconds. What I'm trying to tell you is that the computational time, or the time used to solve the differential algebraic model, is not the same time that we have in real life. 1 second in computational power is not necessarily equal to 1 second in real life. But when we are doing that in real-time simulation, we want to solve the differential algebraic equation at the same time that we are expecting or we are having in real life. And that is a massive computational change. Digital real-time simulation start to be important for power system when we start to integrate information and communication technologies, because the time required for those processes start to be a very sensible variable for decision. And here I can tell you what is the approach that we use typically for real-time simulation. In real-time simulation, we have a workstation that is basically a computer that we use to control the real-time simulator. And the real-time simulator is a very specialized hardware where we solve the differential algebraic equations by taking serious consideration about the time. Inside a classical real-time simulator, there are two powerful hardware for computational purposes. One of them is the classical CPU, but the other one is a FPGA. A CPU is the classical device that you have in your personal computer and solving mathematical problems with a relative flexible time. But the FPGA is a very specific hardware that allows solutions of specific differential algebraic equations in a very fast time, okay? What I'm telling you is that inside the real-time simulator, there are two different hardware, the CPU and the GPU, okay? And when we are talking about CPU and GPU, you need to understand that some equations are solved in the CPU, typically differential equations with high time constants, and then we use very small time constants, and we use the FPGA. For instance, it's typical that we can solve differential equations in order of microseconds using the CPU, and inside the CPU we have the FPGA later solving equations using nanoseconds, okay? I will not go in details into the hardware, but I need that all of you understand how important is the hardware when we are solving the differential algebraic equation, okay? Regarding real-time simulators, there are many flavors, there are many brands, there are many specifications. Today, I will tell you about just two of them because those are the real-time simulators that I have at the lab. One of them is the Typhoon HIL 604, and the Typhoon HIL 604 is coming from Typhoon HIL, that is the manufacturer, and again, inside you have the CPU and the FPGA. And the other real-time simulator that I have at the lab is the Opal RT, the 4510, okay? You can see the links over here, and if you want to get more information, also there are some YouTube channels, some videos on my YouTube channel, okay? When we are talking about fully digital real-time simulators, we have two different options, okay? The two very different scenarios are one, using just real-time simulation. That means solving the model, solving the software, solving the process just in real time. That is what many people call the software in the loop. It's basically one way to assess the computational time required for model, process, software, and so on. And the second most important, and I will say probably the most important for power system analysis, is hardware in the loop. Hardware in the loop imply real-time simulation, but where we integrate some other component inside the electrical power system in the physical layer. What I'm trying to tell you is that we are evolving, we are including the real device inside the loop. And what is the advantage of this? That you are testing your algorithm, you are testing your project, you are testing your idea with the real device inside the loop, okay? What I will talk you now is what we call hardware in the loop. In the hardware in the loop, we have the closed loop, where we have the real-time simulator, and the real-time simulator is sending signals and receiving signals from an actual physical device. To be honest, this is the most realistic simulation that you can do, specifically if you are trying to assess times related to controllers, or for instance, my favorite, protection relays, okay? When we are talking about hardware in the loop, we have one physical device, okay? There are two different approaches that we can use in hardware in the loop. One where we have low power signals, and we call that controller hardware in the loop. And the controller hardware in the loop is basically when we use a hardware, but this hardware is low power hardware. For instance, a controller. You can use an Arduino, you can use a Raspberry Pi, you can use a Texas Instrument or National Instrument device and close the loop in order to test your controller. When you are using controllers, you typically are working with low power signals, and as a consequence, what you need is an input and output board with very low power signals, okay? And the second approach, and probably is the most complex and probably also the most expensive, is what we call the power hardware in the loop. In the power hardware in the loop, we are closing the loop again in the real-time simulation. We are solving the differential algebraic equation by sending real signals, high-power signals to the hardware under test. This is a bit more challenging and a bit more expensive. Why? What is the reason for that? Well, the real-time simulator, the CPU plus FPGA, create signals, but those signals must go through the I/O boards. I mean the digital analogic converter and the analog to digital converters, then go to a signal, we call this a signal amplifier, that there is some power electronics and some sensors, and then you go to the real component, the real hardware that you are testing. The advantages of this is that you are using a real device, you are testing the best way that you can test your approach, okay? Now what I will do is start with few study cases, okay? For instance, I will start with a very short study case, and this is hardware in the loop. But to be honest, this is the specific case of controller hardware in the loop. Last year, with one of my postdoc, Jose Angel Barrios from Mexico, and including one of my former PhD students, Francisco Sanchez, from Loughborough University, we wrote this paper, Framework for Real-Time Simulation, Hardware in the Loop, Applied for Primary Frequency Control. Primary frequency control is one of the control loops that we will find in a real power system, but in this case, we try to enable primary frequency control using battery energy storage. And what was the idea here? Okay, well, we use the real-time simulator. In this case, we use the Opal RT, the OP4510, and inside we have the electrical power system model, and then we use a single board computer, a very cheap single board computer, and we put inside the Arduino the battery energy storage and the frequency controller, the primary frequency control. And then we interchange signals between those. One of the signals, for instance, going from the real-time simulator to the Arduino board was the frequency, and then inside the power production and the state of charge of the battery was going back, okay? And here you can see the real-time simulation. You can see here the electrical signal record at the oscilloscope, and you can see the frequency behavior over here, okay? This is one controller hardware in the loop demonstration, something simple. If you want to read more details, you can go to the IEEE Explorer. I include here the link for the paper. You can download over there. And on the bottom right hand side, you can see the YouTube link. And also you can go to my YouTube channel and watch the video. Power hardware in the loop is something that we have been doing in the previous 2 years. As I say before, one of the main issues when you are using power hardware in the loop is that you require signal conditioning, okay? Signal conditioning is basically a power amplifier. You receive low power signals and you are able to generate high power signals, okay? And in this case, we are using the Typhoon HIL, we are using the Typhoon HIL framework, we are using the real-time simulator, the HIL 604, and then we have this huge elephant here, this signal conditioning that is the universal HIL Connect, okay? This device is able to generate signals at any frequency and high voltage and high currents. And in the case of those, the next study cases, we are working with protection systems, okay? That means that we are able to produce here 230 volts RMS, and we are able to replicate here 5 amps RMS, okay? If you want more information about Universal HIL Connect, you can go to my YouTube channel. There is a full video over there explaining the characteristics and so on. Let me start with one of my favorite cases about power hardware in the loop. One of my favorite cases is what I call relay in the loop. Relay in the loop is a very interesting approach, okay? As you must be aware, protections are very interesting devices. Right now, modern protections, they are totally digital and they have inside a very specific software with specific algorithms that they allow monitoring, sensing, and differentiating between normal conditions and faults, okay? In this case, I am presenting one study case related with the feeder protection relay, the CEL 751, that is a feeder protection relay. To be honest, this scene that I will show you in a few minutes is basically one of the lab that my students take at the lab. They go to the lab and test the non-directional overcurrent functionality of the CEL 751, and using this cyber physical approach using power hardware in the loop, okay? The setup is very simple. We have here at the top the workstation that we are controlling, and we have all the software. Then we have the real-time simulator where the differential algebraic model is solved, and we are sending signal to the huge elephant over here, the universal HIL connect, and finally closing the loop with the Schweitzer Engineering Laboratories, the CEL 751, the overcurrent protection, okay? This looks extremely simple here, and also we include the Ethernet connectivity if you want to modify the settings of the relay, or if you want to record some measurements directly from the relay, you can do that, okay? From the physical point of view, from the cybernetic point of view, we are using the Typhoon HIL real-time simulator framework, and that is basically the Typhoon HIL control center, okay? You have two very important software. One is the schematic that you create your model, and then you have the HIL SCADA, that is where you are interchanging signals, okay? Here, this is the physical representation. On the top, you have the CEL 751. In the middle, you have the real-time simulator, the HIL 604. And then you have the universal HIL connect, okay? This looks pretty from the front, but if you go in real life to the back, you will go to the physical layer, okay? In this case, the physical layer requires some wiring. You are in the actual physical layer, you have the devices, and you need so many cables, okay? As you can see over there, you can see the back of the relay. You are wiring over there the currents and voltage signal, but also the controls and the feedback signals, okay? And then you have the cybernetic layer. The cybernetic layer is basically the layer that you have the model. In this case, we have an electrical model that is represented inside the schematic editor. And then when you compile that and send to the real-time simulator, the HIL 604, you have this SCADA that allow you to do the control of the signals, okay? Here you can create the steady state operation of the system without any fault, and then you can insert the fault, okay? When you insert the fault inside the real-time simulator, you will collect the signal, voltage and current signals during the short circuit, and also you can see here the feedback coming from the relay, the CEL 751 status. You can see that a trip circuit happens and the circuit breaker open, okay? If you want to watch more details, you can go to my YouTube channel and there is a full explanation over there, okay? However, what I want to tell you is that this is a very flexible and very simple way to test the functionality of the overcurrent in this relay, and this allows the student test any kind of fault, location, type, duration, and so on. This is amazing. The student can have the most beautiful learning experience using this setup, okay? Another thing that we have done very few weeks ago is again power hardware in the loop, and we were testing Phasor measurement units, okay? A few years ago, with one of my master students, we create Phasor Captures. Phasor Capture is basically a Phasor measurement unit created with very low cost hardware. As you can see on the right hand side, on the bottom of the right hand side, you have here the Phasor Capture. It's basically 3 single board computers, Arduino, and they are generating signals, Phasor measurements, okay? Here is the physical layer. You have the workstation, you have the real-time simulator, going to the universal HIL connect, and here we are generating signal for voltages. And finally closing the loop, but in this case we are closing the loop using a Ethernet cable. As you can see here on the right button, there is a Ethernet cable going to the workstation, and then we can record over there the Phasor measurement units. There is a video on my YouTube channel if you want to see more details about this, and also one paper is on the review at this moment. There is the reason that I cannot disclose more information right now. Also, one of the things that I am doing right now, one of the things that I can do right now is relay in the loop, but using communication protocols, okay? If you are familiar with protection, communication, and control inside power substation, you must be aware about the European standard. Right now it's a universal standard, the IEEE 61850, okay? It's basically a standard that creates the model and the framework for communications inside the substation, and basically for protection automation, okay? This concept allow to change the way that we are wiring, or the way that we are connecting measurement devices and protection devices. Based on IEEE 61850, we can use what we call the emergent unit. Instead of collecting voltages and current from current transformer and voltage transformer using copper wires, we can use fiber optic and move inside the substation just digital information coming from the signals, okay? What I'm trying to tell you is that in a new digital substation, we have what we call sample values. Sample values is the conversion of the instantaneous values of voltages and currents that they are translated into digital information, and then they can move inside the substation using a classical Ethernet or a classical fiber optic inside the substation. And also there is another communication protocol that is called the GUS, that is the protection messaging, that allow you to, for instance, define the status of the circuit breaker, send or receive signals of opening or closing those circuit breakers, okay? What we have done in recent time is testing relays using this amazing approach, using the IEEE 61850, and here you can see the configuration that we are using, okay? We are having the workstation. With the workstation, we are connected using a classical Ethernet copper wire to a switch. From the switch, we are going again using Ethernet communication protocol to the real-time simulator, in this case the HIL 604, and then from the same switch, using just very digital signals in this very specific communication protocol IEEE 61850, we are communicated directly using digital signals to the protection relay. In this case, we are using one of these amazing relay, the ABB REDS 640, that is fully able to receive sample values using this communication protocol. What is important to know is that Typhoon HIL has a tool chain that allow you generate and receive this kind of communication protocol, okay? If you want to learn more about this communication protocol and the test that we have done, you can go to my YouTube channel, and there is a very specific video talking about the cyber layer of this Typhoon HIL control tool chain, okay? Finally, what you need to do is configure your relay. And in this case, you need to go inside their physical relay using the software, in this case the ABB PCM 600, and talking in the relay hardware, the RED 640 can be configured in order to receive the signals, the measurement signals coming from the fiber optic using the sample value subscriber, okay? We have done those tests. Results will be published very soon, and I cannot give you more details at the moment, okay? Well, we have been here almost 1 hour. I didn't include the delay at the very beginning, but we are here probably for around 55 minutes, and it's time for a closure, okay? What I want to tell you on the closure of this presentation is that digital technologies are changing the way that we think about electrical power systems. Electrical power system will not be longer just electrical, because we are integrating many other technologies, communication, computation and so on, but also in the future we are integrating so many other energy kinds. For instance, we are including transportation, we are including hydrogen, we care about cooling and heating. That means that the electrical power system is integrating with other energy systems. That is increasing the complexity of the physical layer. From the digital technologies, networking and computation are creating new challenges, but also new opportunities in the electrical power system. What I'm telling you is that the cyber layer is creating new opportunities for us and new challenges for very old engineers that they must adapt to the new technologies. Okay, they are opportunities for cost reduction, emission reduction, also start to stop the use of so many oil-dependent technologies and increase or reach 100% penetration of weather-dependent technologies like PV and wind power. Okay. However, this new form of cyber-physical system requires to think about again the way that we are performing studies in electrical power system. We cannot keep using offline simulation, especially when we are having so many power converters integrated in the electrical power system. The dynamic of the electrical power system is becoming more and more, let's say, faster and faster, but also complex and more complex again. That is the reason that we need to think about the use of modern and very different technologies, okay? CoSimulation, real-time simulation, multi-domain simulation, and so on. Okay. Well, this is the close for my presentation today, and I think it's time for some questions, and I can see already there are a few questions over there. However, I will give the pleasure to Conrad to start the question and answer session. Thank you.